to see in the YouTube.
Yes, it is. Skin is coming.
Yes.
It is okay. Skin is coming and voice is also coming.
Oh, thank you for confirming. So once again, welcome to the week 2 live session of Quantum Chemistry of Atoms and Molecules live session. Today, we will not do any I think discussion about the week 1 lecture because what I saw is that week 1 and 2 assignment is still left to submit on maybe the last date I guess is tomorrow. So there is no meaning of solving that today. But what I am planning to do is that yesterday in the last session, actually, I was solving some numerical problems regarding de Broglie's theorem and the photoelectric effect. So we will continue with that. As I have already shared those questions in the previous day, so we will solve those and we will solve some tutorial problems also if time permits. So let us go ahead. Uh, so these are the problems that we already almost solved up to 8.6b, I guess. We have solved. We did not solve 8.7a and 8.7b. That we will do it today. And we will solve this problem. These problems are actually from Atkins Physical Chemistry book, 8th edition. So this we will try to solve. Most of the problems are based on de Broglie's theorem, or you can say de Broy's theorem, and the Einstein's photoelectric effect, and some problems are from operators. So we'll also do them. And what we will not do today is another set of questions from mostly from particle in a box theorem, which you are right now learning, and the assignment is I think also due for that. Some numerical questions are due, so that we will do. So these questions are eventually going to help you in solving them. But what I will prefer is that I will try to solve this next week so that you get a wholesome idea, and we will also discuss some more problems for particular. So with this problem, so we'll mainly try to solve 8.7a, 8.7b, and from 8.8a to 8.14b, I'll try to make it interactive so that you can also take part into the discussion how to solve them, and we will solve them together. And one more thing is that I will try to solve this one tutorial one problem based on mainly from on the quantum chemistry operators. Uh, but to start with, this tutorial problem is actually set by the faculty members of Department of Chemistry at IIT Bombay. So there is a course chemistry 101 CH101. Now it is called CH111, which is taught for the first year BSc student, basically BTech students, for all the engineering section and chemistry also. So, this is a part of that tutorial problems, and I'm taking permission from Professor Ananda Datta so that I can discuss this problem with you. So, all the credit goes to the faculty members, basically, to our department. So, this I will try to solve after those problems, and if we can't solve it, then this will be your homework too, and to try to solve it. I will share this tutorial with you. So let us begin. So we'll start by solving this 8.7a and 7b. Arup, I think you are still there. And so did you try to solve this problem? Did you join the last class?
Not last class. I engaged in a different class,
Okay.
symmetry and group theory. The what
Okay.
both classes are scheduled at the same time.
Okay.
Uh,
Okay.
there is a problem.
So actually,
But I see the recording.
okay. 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 That means that was the problem actually. What happens is that those two courses are run by two different discussion sessions are run by two different PMRs. So most of the time, what happens that this is a preferable time for both of us. Other time we are busy in research work, but if you are missing something, you can always go back to the recording files. It will be available. But yes, we want you to be attend these classes so that this can be an interactive session. So I will ask the PMRF means the team if that can be resolved. That issue can be resolved. Maybe I can shift to 5 to 7 slot. I will check with them and let you let you posted in the discussion session maybe. So you will eventually know that. But let us start with these questions. I hope you have seen this as you told that you have already gone through the previous week's lecture. So these are actually based on de Broglie's theorem. So that is the equation is where is my cursor? So mostly based on the de Broglie wavelength is a wavelength of. So what we discussed that de Broglie actually that de Broglie wavelength belongs to all the particles. So there would be a matter wave. So for every matter there is some particle-like behavior and some wavelength-like behavior. Wave particle duality is there. So for every matter or even what we see in macroscopic cases, there could be some wavelength associated with it. But so that wavelength is given by h by p. P is momentum, or you can always say h by mt, where h is Planck constant. So this is an empirical constant which is given by 6.626. This came from, I guess, some empirical equation to fit the black body radiation problem, and from there this constant came up. So the unit of Planck constant is joule second. Another way to say is kg meters per second inverse. Okay, so this is another way to write the unit. We will be try to I will always try to tell you what is the unit so that you don't mess up. And if during solving of the numerical problem, if I am making any mistake, please means knock me that there is some mistake. Okay. Let us start. So the first problem, as you can say, and another one I was telling that we are following that photoelectric effect problem, where the total energy that is falling as a quanta of photon is falling onto a metal plate, and from there, so each metal will have some work function associated with it, or the binding energy, you can say, and above the binding energy, if your energy falling onto the plate is above that binding energy, then electron will be ejected. One electron will be ejected for one photon, and that electron will have the kinetic energy. So that kinetic energy is suppose half mv square, as you know. That will be equal to the total energy falling, that is hc by lambda mostly minus work function. So phi is work function. So basically, based on these two formula, we will try to solve today's problem. So let us start. So the first problem 8.78 says that a sodium lamp emits yellow light, that is 550 nanometer wavelength. How many photon does it emit each second if its power is 1 watt and 100 watt? So as you can see, which equation we are going to use? So mostly we are so actually not any of them, but in a similar problem, I will just write it here. 8.78. So the energy per photon will be given by hc by lambda, right? So the energy of each photon will be hc by lambda, and we already know h is 6.626 into 10 to the power minus 34 joule second. C is the speed of light in vacuum, that is 3 into 10 to the power 10 meters second inverse. So I have made one mistake. 3 into 10 to the power, if I write 10 to the power 10, then it is centimeter per second. But if I want to write it in terms of meter, then I have to write 10 to the power 8 and divided by lambda. And it is said that we are using yellow light and lambda is given 550 nanometer, right? which is again 550 nanometer. If I want to transfer it into the meter, then I have to multiply by 10 to the power minus 9. So this is my energy per photon. So what is the energy per photon? Let me calculate. You can also calculate with me. So 6.626 into 10 to the power minus 34 multiplied by 3 into 10 to the power 8 divided by 550 divided by 10 to the power minus 9. That is, we are getting somewhere around 3.614 into 10 to the power minus 19. What would be the unit? As you can see, meter would cut, second inverse will cut with second. So obviously energy will be in joules, right? This is in joules. Now it is said that, let us go back to the question, that so this is the energy of each photon of this sodium lamp. Huh? So how many photon does it emit in each second if the power is 1 watt? Okay. So what do you mean by power 1 watt? Power is work done per second. So actually your 1 watt means it is emitting 1 joule per second. Right? So the power is 1 joule per second. That is 1 watt. So at in 1 second, the lamp is emitting 1 joule of power. And we already know what is the power of each photon, right? This is the power. So how many photons? So the number of photon emitted will be 1 joule divided by 3.614 into 10 to the power minus 19 joule. So as you can, to be a rough estimate, it will be something around um, we will do a rough estimate and just divide it. Something around 2.76, if I'm not making any mistake. I'll just check once. Huh?
Yes, it is okay. Right.
It is okay, right? Okay, so it is something around 2.76 or 77, we can say, into 10 to the power 18. Uh, as joule will cut, so it will be something like that. Okay, so this is for 1 joule. Now, uh, what about 100 watt? Can you tell me what you have to do for 100 when the power is 100 watt? So that time actually,
Just multiplied by 100.
right, right. That means it is emitting 100 joules of power per second. So I'll not do that. So let us go back to the question maybe. Yes. So that we'll be able to do. Similarly, 8.7b also tells us that a laser used to read CDs emit red light. So mostly there, the question have many things, but you have to see that what are the factors you have to take in. Suppose uh, 8.7a and 7b are basically the same question. One is based on sodium lamp and this is about CD. You don't have to be confused. You have to just take the lambda here. Nothing else. So red light of wavelength 700 nanometer, a laser can read. Right? How many photons does it emit each second if the power is 0.1 watt? So again, that means you need to calculate the energy of each photon. Then you need to see that at 1 second it will emit 0.10 joule. Then how many photons are there? Then put power divided by energy of your each photon. So that would be your number of photons if we emit, right? Easy to solve. So let us not do that. We can go to the next question. So the next question, 8.8a. Again, as you can see, it is talking about the work function of metallic cesium is 2.14 electron volt. Calculate the kinetic energy and speed of electron ejected by light of wavelength 700 nanometer and 300 nanometer. So this is based on Einstein's photoelectric wave, right? So work function is 2.14. So you need to provide an energy greater than 2.14 electron volt so that your electron will be ejected. Right? So from so as we are discussing photoelectric effect, so the two things to remember that one is per photon, per for each incident photon there will be one ejected photon if it passes through the work function. So it is not like that one photon will fall and two electron will be ejected. That is not the case. This is one is to one. That is one thing. And so let us see. First, tell me that if you seeing it that which wavelength have higher energy, 700 nanometer or 300 nanometer? Can you tell me?
300 nanometer.
300 nanometer will high energy, right?
Yes.
Because hc by lambda, it is just inversely proportional to lambda. So let us start from the first one, right? Uh, Here 8.8 is right across. So energy of photon, again where the lambda is 700 nanometer, that is again similar hc. I'll just write it joules again into 10, 3 into 10 to the power 8 meters second inverse divided by 700 nanometer is 700 into 10 to the power minus meter, and just quickly calculate it. So it is something around 2.83, or I should write 84839 it is. So I'll just take two decimals, 84 into 10 to the power minus 19 joules, right? As we see meter will count, second inverse second will count. So, but as you remember that phi work function, work function is nothing but you can say binding energy of an electron, equivalent, right? That was I think given 2.14 electron volt. So here we also want to know how much 1 joule is equal to how much electron volt. 1 joule is equal to, so actually uh, 6.242 into 10 to the power 18 electron volt. And if someone wants to know the opposite thing, obviously they can take an inverse of it. 1 electron volt is this we often know 1.6 into 10 to the power minus 19 joules, right? So we will actually convert it to electron volt. Maybe better to convert it into the joules, right? 2.14, 2.1. How much is the work function? 2.14 into 1.6 into 10 to the power minus 19, and that is 3.42 into 10 to the power minus 19. So see, here comes one thing, that the thing I was talking about, that can you see that the incident photon has an energy of 2.84 into 10 to the power minus 19 joules, right? But the work function is 3.42 into 10 to the power minus. So that means your work function is greater than your incident energy. So do you think the electron will get ejected?
No.
No, right? So so if it could have ejected, then the energy could have negative, but that is unphysical, right? So electrons will not eject at with the photon of lambda is equal to 700 nanometer. But as you correctly told earlier that lambda is equal to 300 nanometer has a higher energy. So let us see what will be the energy of the photon with 300 nanometer. So I'll just directly write it. So that is I'll, I'll write I'll do it in my calculator, but write it directly as you already have the equation hc by lambda, right? So it is coming as 6.63 into 10 to the power minus 19 joules. Okay. So it is coming something like that. So here obviously your incident energy is more than that of the work function. So your kinetic energy, so your electron will be ejected. So for each photon, only one electron will get ejected. So your half mv square. That is your kinetic energy of that electron. Kinetic energy of electron, as you know, is your 6.63 minus 3.42 into 10 to the power minus 19 joules, right? So that is actually, I'll do it.
3.78.
It's right. So 2, 3, something around 2, 1, 4, 6 is at 2, and 3.21, right? 3.2 into 10 to the power minus 19 joules. And you already, so we need to calculate, I think, the velocity, right? Or what is the thing we need to calculate? Kinetic energy and speed. So this is the first part. Obviously, we get it. So this is the kinetic energy, 3.21 into 10 to the power minus 19 joules. Is this correct? Or I guess this is correct.
Yes,
3.21.
correct.
So
3.2.
this is
Yes.
so this is the kinetic energy. Now we already know that mass of electron is how much? 9.3 into 10 to the power minus 31 kilograms. So the velocity will be something as so we got half mv square is equal to 3.21 into 10 to the power minus 19 joules. So your V will be something around 3.21 into 10 to the power minus 19 joules divided by, so multiply by 2 and divided by 9.3 into 10 to the power minus 1 kilograms. Now, if we break down the unit again, so joule is what? Unit of energy, right? So, what is energy or what? So, that is your force into displacement, right? So, so these are the actually this is how I remember the how to break down the unit. So energy is work done. Sorry, energy or work done will be same, right? So work done is your force into displacement. Force is Newton and displacement in meter, right? And again, how do we break down Newton? Newton is force. So the second law of Newton, uh, the laws of motion, that your force is mass into acceleration. So mass is kg So I am always taking SI units. So kg into meter second to the power minus 2, right? So this is my joule. I am having take, so this is kg meter square second minus 2. So what I am getting here. So first of all, I can easily think of this as 3 and this is as 9. So suppose we are doing it for some competitive exam, then you are not really going to do the 3 by 9, right? So you will think of it as a 3 by 9, 1 by 3, less than that, but that you can do always in competitive exam. So Arup, in which year you are studying in BSc, MSc or PhD? Can you tell me that?
No, I have completed my MSc and I am doing some job.
Oh, you are into the job. Okay, okay. So, okay. You have calculating in calculator actually. You can always do it. I mean, a big number is coming.
The whole multiplication and division is under root.
Yes, I forgot it. I put the bracket, but I forgot to keep the 1 by 2. Thank you.
This is about 8.4 into 10 to the 5 meter per second
8.4
into 10 to the 5 meter per second.
10 to the power 5 or 10 to the power 6. I'm getting something around uh, 8.3 into, no, you are correct, 10 to the power 5. 8.3 into 3.234. 8 into 10, yes, 8.3 into 10 to the power 5. You are correct. 8.3 or 8.4? And as you can see from the unit also, I think someone is writing something in the chat box. I'll just quickly check it. Um, why, uh, um, Arup, you can hear me, right?
Yes, I have no problem. Yes,
Yes. So maybe I'll, okay. So we'll get back to our YouTube business. So 8.10, and obviously the unit is now meter square second minus 1, and half of that kg is gone. So it is meter second unit. Obviously unit of velocity. So this is going to be the velocity, right? So similarly, I guess one will do so as you can see for 700 nanometer, no electrons will be ejected. For 300 nanometer, the electron will be ejected. And then 8.8b, similar problem one can do it eventually. He, from the values given, the phi is almost similar, right? The work function is almost similar. So I believe that with 650 nanometer again, the electron cannot be ejected. Means one can obviously do the calculation, but as the values are close, what I am thinking that with 650 nanometer, uh, again the energy of 650 nanometer wavelength will be lesser than that of the work function given. So the electron will be ejected only with this wavelength, 195 nanometer in the second problem. So that can be that is up to the students to do. Let us go back to let us get to the another question. The next question, 8.9a. So the question says calculate the size of quantum involved in the excitation of a an electronic oscillation of period 1 femtosecond. Second, a molecular vibration of period 10 femtosecond. A pendulum of period 1 second. Express the result in joules and kilojoules per mole. The question is a little bit confusing, but let me tell you. Here we need to means calculate the size of quantum means we need to calculate the energy of quantum. So obviously energy of quantum we know hc by lambda, right? Or in other words h nu. So where nu is frequency and frequency is related to the oscillation period, right? Or this time. So let us what I'm trying to tell. I will write it here. 8.98. So energy we know is h c by lambda. We can write it like this, or we can write h into nu, where nu is frequency, and we can always write frequency in term of 1 by tau. Nu is frequency, that is 1 by tau, that where the tau is oscillation period or period of oscillation. That is a means okay. Um, Now tau is given. So for the first problem, for an electronic oscillation, as you can see also, the electronic oscillation, the period is 1 femtosecond. So the how much will be the energy? So in case of electron, tau is 1 femtosecond. That is 10 to the power minus 15 seconds. So obviously energy would be 6.626 into 10 to the power minus 34 joule second and divided by 10 to the power minus 15 second. Second cut, and it will be 6.626 into 10 to the power minus 19 joule. Right? So this is in joules. So they want answer in joules and I guess kilojoule per mole, right? Kilojoule per mole. So before, so this is in joules. So how much will be in kilojoules? Obviously, 6.626. We need to divide it by 10 to the power minus 3. Sorry, divided by 10 to the power 3, and that's why it will become 10 to the power minus 22 kilojoules. Now this is for one electron. What about 1 mole of electron? 1 mole of electrons means Avogadro number of electrons. So that is, we need to multiply it with Avogadro number to get for 1 mole of electron. The energy for 1 mole of electron, that is 6.626 into 10 to the power 22 into 6.023 into 10 to the power making mistake, not minus 23 but plus, right? 23, and my unit will become from kilojoule to mole inverse because the Avogadro number ANA is actually 6. So this, in terms of number it is 6.623, but per mole it will be in per mole. So I'm not writing it as this. And you can see from here, and what will be the value? So 6.3 something like 6.63 into 6. When we are in a competitive exam, we'll just see. So when in competitive exam, we'll just see we treat it as 6.6 into 6, right? And this is actually minus 22, and so it will be something like 10 kilojoule mole inverse, right? Something like that, and we can do it by just by looking at it. Let's say 36, 36, 39.6. I guess something like this will come up, and 396. But when we need to do it for some numerical problems, then we have to use our calculator. 6.626 into 6.023. So we'll get something like, actually we are getting 399.08 kilojoule per mole. I guess I have not done any mistake in the calculation, right? Is it correct for you? Do you find it justified? I'll just remove this.
Okay, it is correct. It is correct.
And I'll just remove this part because I have just written it for sake of clarity. I have just multiplied 6.626 with 6.023 and obviously the other thing. So when we are not doing that, we are getting something around 396, which is close anyway. So if it is a multiple choice question, then we'll just see what is closest to 396. Obviously, if the paper setters are something like that, they will give 399 and 396, then it will be tough for us. I hope that will not be the case. Anyway, so this is for 1 mole of electron. What are the other things given? The other thing is given a molecular vibration. So molecular vibration of period of 10 femtosecond. Similarly, the energy, as you can guess, it will be for a molecular vibration. I'll not write down the exact, and I can write it down, right? So it will be, so instead of 1 femtosecond, it is 10 femtosecond. That is mean 10 to the power minus 14 seconds. So, so for molecular vibration, the energy will be something like 6.626 into 10 to the power minus 20, right? 10 femtosecond. If it is 10 femtosecond, it will be 10 to the power minus 14. So that will lead to this. Now rest is same. We need to convert it into the kilojoules, and then we need to calculate for a Avogadro number of molecules that will lead to kilojoule per mole. I hope that is clear. And the next also you will be able to solve a pendulum of period. So there we need to think of Avogadro number of pendulum or like such like that. So we can think of like the 1 mole of chairs, 1 mole of pendulum. That means Avogadro number of chairs, Avogadro number of pendulum. Even though it is not, even though it is unphysical to think about means that many chairs or pendulum, but still, that's what they want. So the second part, 8.9b, is the same question, right? So calculate the size of quantum, the size of the energy of the quantum with this electronic oscillation, molecular vibration, and a balance wheel of 1 millisecond. So from there, actually, what we can understand is that when your period is actually increasing, as you can see, when the period is increasing, your frequency is decreasing, right? If the frequency is decreasing, there your energy is also decreasing. So you can think like that, a balance of wheel of period 1 millisecond will have lesser energy, right? Than that of a electronic oscillation with 2.5 femtoseconds. Okay. Now let us go to question number 8.10a. Similar question, calculate the de Broglie wavelength of a mass traveling at this velocity, same traveling at higher velocity, and a helium atom traveling at 1000 meter per second, a typical speed at room temperature. Let us do that. And so the purpose of these questions are not to just calculate, but also you have to think that what we can learn from this question, that what is actually happening when the what will be happening to the d wavelength when the mass is same but the velocity is increasing. When the mass is also increasing, velocity is also increasing. So that is what is the purpose of this question. Okay, not just to calculate the thing. So let us do that. 8.10a. We just write the formula again, that de Broglie wavelength lambda is h by p or h by mv. Right. So now what is given? That calculate the wavelength of a mass of 1 gram traveling at 1 centimeter per second. So mass is given. The first mass is 1 gram. That is, I will convert it into kg, right? And velocity is 1 centimeter per second. I guess I will again check. So that means 10 to the power minus 2 meter second. Better it is always better to go to the SI units for this kind of question. 1 centimeter per second. So, and we all know what H is. So what will be the lambda? 6.626 into 10 to the power minus 34 joule second divided by 10 to the power minus 3 kilograms 10 to the power minus 2 meter second. And obviously from here we know joule second is nothing but I will just directly write joule second is nothing but kg meter square second minus 1. Because second minus 2 and second was there, so it will become second inverse. Second inverse gone. Meter, one of the meter gone. Kg, one of the kg gone. So meter is there. So below it is 10 to the power minus 5. So it will be easy, I guess. 6.626 into 10 to the power minus 29 meter. Right? So this is the wavelength of that particular mass where the mass is 1 gram and speed is 1 centimeter per second. See, the wavelength is very, very small. It is not even in the angstrom, right? It's very, very small. So, what do you think? Can we able to see this wavelength, or can we actually feel the wave? Can we actually see the wave nature of this particle? What do you think?
No, we can feel the wave nature of it
Will
because
not
of
be able to, because it is so small. There is no such diffractometer or no such atomic that diffractometer actually of that small quantity that can diffract this wavelength. And if something cannot diffract, we won't be able to see the wave nature. So we won't be do it for this system. But what if the velocity of the same mass becomes 100 kilometer second inverse? So that is actually 10 to the power 5 meter second inverse. I don't think there would be much change, but let's see. Lambda will become 6.626 into. I will not write the unit right now because we are almost using the same units. So unit will be meter. So 10 to the power minus 3, 10 to the power 5. So it is 10 to the power 2. So actually when the speed is increasing, the wavelength is even decreasing. Right? The same mass, when the speed is increasing, actually the wavelength is even decreasing. So one thing means we obviously if we can't see the wave nature of the previous particle with this speed, we won't be able to feel the wave nature of this also. What about a mass of helium atom? I guess the next question was about helium. Yes, the part C was an helium atom traveling at speed of 1000 meter per second. Now, for a helium atom, mass of helium atom is in atomic unit. It is given by 4.002 atomic mass unit, right? Which is actually in kilogram. So we need to know this uh, conversion techniques, unit conversion. So that will lead to kg. And how much will it be? Just see, 4.002 into 1.66 into 10 to the power minus 27, and that is something around 6.64 into 10 to the power minus 27 kg. So mass of helium is this. Now what will be the lambda associated with this? 6.626, and the velocity is uh, 1000 meter, what I remember, meter second equal 6.626 into 10 to the power minus 34 divided by the mass 6.64 into 10 to the power minus 27 kilograms. I'm not writing the unit, but it is always advisable to write the unit as we are using the same set of units, so I'm not really using that. But that is not a good practice actually, to be honest. So what we can see from is there 6.6 to 6.6 almost same. We can treat them as 1. Actually, less than 1, I can write 0.99 if I don't have to want to use the calculator, right? 99 something like that will come. And what about the order of 10? 10 to the minus 34 and below is 10 to the minus 24. I guess we are going to get 10 to the minus 10 meter. And as you can see, we will get something around 0.0999 angstrom. What do you think? Yeah, can we see these? Can we get the wave nature? We can see the wave nature of helium. Will we be able
Yes,
to? Yeah.
we get the awareness, sir.
So we will require some atomic so the distance between two atomic planes to be in 1 angstrom to diffract this, right? 6.64. Actually, it is 0.997. So we are close.
Okay.
So it is close to
The
one
one,
angstrom. So we'll need diffraction length of 1 angstrom to see the wave nature of this. Okay. So
the
that's what.
uh,
Yeah.
one thing that comes into my mind sometimes, whenever wavelength is decreasing, the energy increasing.
Yes.
Energy of gamma, wavelength of gamma ray is near about 10 to the minus 19 meter, and
Okay.
we are getting the wavelength of one gram object. It is about 10 to the minus 19 meter. So in
Okay.
that sense, it can be correlated that energy of that wavelength is much much higher than gamma ray.
Yes. True. Energy of gamma is higher, right? It can pass through. I guess it can pass through. Alpha particle can't pass through a sheet of what was like a sheet of paper. I don't exactly remember
The
that.
gold plate.
Gold plate or maybe that lead sheet of lead. Uh, but gamma, I guess, can pass a few centimeters. What I remember, I don't remember the exact length or width of that lead sheet. But let us check. Let me check in mobile maybe that comparison of energy between gamma and actually this helium atoms or helium ions will actually similar to that of alpha particles, right?
Alpha particle.
So in that terms, um, gamma rays of pure energy, gamma rays are similar to visible light. Mm, radioactive hazard of energy. Okay, let us check. Let us go back to the discussion and the next question, 8.10b, right? Calculate the de Broglie wavelength of electron accelerated from rest to a potential difference. So the question is again means a little bit different, but easy. So actually, the energy or kinetic energy of an electron accelerated through a potential difference of 1 volt is 1 electron volt. What I'm trying to say, 8.10b, right? The kinetic energy of an electron at 1 volt is 1 electron. Obviously, that is 1.6 into 10 to the power minus 19 joule. So, what are the things given? So, you know so if it is passing through 100 volts, so you know the inner kinetic energy is 100 electron volt. If it is passing through 1 kilovolt, that is 1000 volt, the energy is 1000 electron volt. It is passing through 10 to the power 5 volt, then the kinetic energy is 10 to the power 10 to the power 5 electron volt. So you know the kinetic energy. You need to calculate the de Broglie wavelength, the lambda. So what is the relationship between the lambda and the kinetic energy? So again, lambda is h by mv. Your kinetic energy is half mv square, right? So if I multiply m in numerator, I need to do same in the denominator, and it will become m square v square by 2m. That is nothing but your p square by 2m, right? That is your momentum. Here it is h by p, right? P is mv. So that is your kinetic energy. Now, what is your momentum? Momentum is nothing but root over 2 into mass into kinetic energy. Right? So you just need to put lambda is equal to Planck constant divided by root over 2 into mass into kinetic energy. So that is the relationship between the lambda and kinetic energy. Now obviously the first one was 100 volt, I guess, passing through a potential difference of 100 volt. So the kinetic energy is, so kinetic energy in the first case is 100 electron volt. That is 100 into 1.6 into, as I told, better to go to the SI unit, joule. So 1.6 into 10 to the power minus 17 joules. So what would be the wavelength? That is 6.626 into 10 to the power minus 34 joule second divided by root over mass of electron, obviously 2 into 9.3 into 10 to the power minus 31 kilogram multiplied by the kinetic energy 1.6 into 10 to the power minus 17 joules. So we need to break down the units here, right? So joules, I'll do just that. So the first part will be in the numerator kg meter square second minus 1, and in denominator there is a root over, so I'll use that kg, and we have joules, right? So that is kg meter square second minus 1, second to the power minus 2. So actually we are going to get, so kg into kg, square of that kg will come up, kg will gone, right? So I'll just do it from here. Kg, this is gone. Meter square will be uh, meter second minus 1. So 1 meter and second inverse is going to gone. Obviously, we will going to take with meter. So that is obviously very easy if you are, I mean, thinking in terms of lambda, but it is always better to do your unit conversion. maybe sometimes a factor of 10, factor of 1000 may get missing, and you are going to start with the wrong answer. So always in physical chemistry, we have to do this unit conversions. So I'll just quickly calculate it in calculator. 10 to the power of 34 divided by what? Something like I'm getting something like 1.214 into 10 to the power minus 10. So that is in meter. 214 into 10 to the power minus 10 meter and 1.2 angstrom, 214 angstrom. I hope my calculations are right, but this
Right.
kind, this is what I'm getting. Thank you for confirming. 1.14 angstrom, 1 angstrom, something like that is going to come. What about if the now the voltage is one kilovolt, that is 1000 volt, then my kinetic energy would be in the second case, if my
10
kinetic
times.
energy,
Kinetic
yes,
energy will be 10 times.
uh, 10,
10 times means lambda 10.
yes,
Lambda
kinetic
means
energy will be 10 times. What about my lambda? Lambda will be something
lambda
like, obviously will decrease to the extent of root 1 by root 10,
divided by 10.
root 10, root of 10, right? Because the kinetic energy is under
Ah,
root.
yes. Yes, root
So
of 10. Root of 10.
yeah. And then obviously, if my kinetic energy is even higher, this C 10 to the power 5 volt, then it is again uh, below that, right? It is going to be root of 10 to the power 5. Yeah. So my de Broglie wavelength is going to decrease if my, as what we have already discussed, if my kinetic energy is higher. Anyway, now what about the 8.11b question? So that is the first question we are dealing with, are operators. The question says, show that the linear combinations of a plus ib and a minus ib are not Hermitian if a and b are Hermitian operators. So before solving this question, let us remind the postulate, one of the postulate of quantum mechanics, that tells us that all the quantum mechanical operators are going to be linear and Hermitian. So we have a mathematical definition for Hermitian operators that I am going to write soon, but there it is used sometimes as definition, but that is not true. It is a actually a postulate, you can say, or you can say that is coming as a result of this postulate that uh, the eigenvalue of the Hermitian operators associated to Hermitian operators are always going to be real. So as we know that all the physical quantities, suppose position, physically observable quantity, position, kinetic energy, these are always real quantities, right? So so if our operators are Hermitian operators, then obviously those have the information, those are going to get the information about this energy or position or momentum, and that will come in terms of eigenvalues, and obviously eigenvalues are going to be real. So Hermitian operators have real eigenvalue, but that is not a definition. That is often sometimes we make a mistake that if someone asks us that what is the definition of Hermitian operators, we say the operators whose eigenvalues are real, those are Hermitian operators. That is actually not true. So, what is the definition of Hermitian operator? So, the mathematical definition, I think it is 8.11b, right? 8.11b. So, mathematical description of Hermitian operator. Suppose A is a Hermitian operator and we have psi I and psi j, and we will have a integration all over sum all over the space, right? And obviously psi j is complex conjugate. Then the mathematically A is when A is Hermitian, so we are going to get something like this: psi I star A psi j d tau and complex conjugate of total integral. This is the mathematical definition. Here it is given that A and B are Hermitian operators. So obviously for B we can write similar set of for a similar set of eigenfunctions. So now we are talking about B, right? Psi I d tau. This is the mathematical definition. Now we need to prove that the linear combinations, I'll write it together, A plus minus IB, if it is going to be a Hermitian operator or not. So to fulfill a Hermitian operator means the definition of a Hermitian operator. So if it is an Hermitian operator, then uh, it has to be something like this. For a same set of suppose we are working with the same set of eigenfunctions, so I should not use the triple bracket because this actually confuse us with the commutatorship. So we just use the first bracket A plus minus IB. I am performing for the both the linear combination and together. So I'm using this psi j star psi I d tau is psi I star A plus minus IB psi j d tau. So if this is Hermitian, then we will fulfill this. So this is our right hand side RHS and this is our left hand side. Let's see if left hand side is equals to the right hand side or not. So we'll just use the left hand side. I hope you are following.
Yes.
So this part is psi j star. So as they are also linear in terms, so we can break down into both, right? So we will do it A psi I d tau plus minus psi j star I will take outside. We will have B. I is iota, inverse of minus 1. Sorry, not inverse, square root of minus 1. Psi I beta. Right? So as we already know, A and B are Hermitian, right? So from there, actually, we can use this equation, so say for equation 1 and 2. From there, actually, we can replace this in terms of this psi I star A psi j d tau complex conjugate of all plus minus I psi integral, obviously I cannot miss integral, psi I complex conjugate of that d psi j d tau complex conjugate of all. Now what I am going to do is I am going to put this, insert this I inside the complex conjugate. Then what I am going to get? Minus 1. What I am trying to say is psi I star. I will just write this part as it is. What I am trying to say, if I want to insert this I inside this star, then I will have to multiply with a minus 1 here. So that will lead to minus plus double bracket I psi. Again, I will write the rest of it as it is. I hope my writing is clear so that you are able to follow. And now I will take the whole thing
Yes,
inside
yes.
inside the side d tau minus plus, actually that, so this is nothing but IB. Again I can write it like earlier I took I outside of that and now again I am taking it inside with minus I j d tau, and then again I'm closing the second bracket and taking a complex conjugate of all. Right? Ultimately, what do I have here? So if I have to make it this, so actually we have psi a star A minus plus IB IJ beta complex conjugate of C. Now what we are going to see that actually this we are getting from left hand side, we are getting something where the in between it is A operator minus plus IB, which is not equals to the RHS, right? So our LHS is not equals to RHS. So our these linear combinations A plus IB plus minus IB here. So for A plus IB, we are going to get A minus IB inside. And for this combination A minus IB, we are going to get A plus IB inside, right? So this is not Hermitian. Okay, so this is a lengthier way to do it. Another shortcut process is there. I will also mention it here to take a Hermitian conjugate. So if my A and B are Hermitian, so this is known as this dagger is actually known as Hermitian conjugate. So this is if Hermitian conjugate of A is A, then A is Hermitian. Okay. So so if we see what does this plus minus IB now in terms of this shortcut method is that is actually A dagger plus minus IB dagger. A dagger is A because we know A is Hermitian. What about plus minus I? I is constant, so it is I dagger into B dagger. A I dagger is minus 1 into I. So that will eventually lead to minus plus I, and B dagger is B because B is Hermitian. So again you can see you are going if you take a Hermitian conjugate of A plus minus IB, you are going to lead with A minus plus IB, which is not same as the operator you started with. So this is not Hermitian. So this is a shortcut method, and this is the way if you go the lengthier method, then you can go with it. Okay. So it was given that proof A plus minus IB are not Hermitian. We have done it. I hope there is no doubt. Uh, if there is, you can speak, and if not, then we can move to 8.12. The next question. Can we move to the next question? Or
Yes,
we
yes,
okay, okay,
you can move.
okay. So the next question 8.12a is calculate the uncertainty of in the speed of ball of mass of 500 gram, that is half kg, that is known to be within 1 micrometer of a certain point on a bag. So obviously minimum uncertainty, that means it is a question about Heisenberg uncertainty principle, and you know the one of the formula regarding that, that is uncertainty in position multiplied by uncertainty in momentum is greater than equals to h cut by 2. That means one of the another way to say is that we cannot measure momentum and position of a particle, of a quantum mechanical particle, to be precise, of a quantum mechanical particle, to be honest, any particle. But for a quantum mechanical particle, we cannot measure the momentum and the mass, the position at the same time, or with the same precision, to be honest. Uh, and that is not a limitation of the instrument. That is actually a inherent problem. That is not due to some limitation of any instrumentation. That is one point to remember. Another thing is that this is not only true for position and momentum. That is true for any operator which will commute, which will not commute actually, which will not commute. For any of those operator, you can't measure the, the you can't measure them simultaneously. So there will be some uncertainty. So here in this question, it is given that the minimum uncertainty of the speed we need to calculate. So mass is given So there is some uncertainty in the momentum that is due to the uncertainty in speed, and it is also given that uncertainty in position is given. How do we know that is uncertainty in position? Because that is not written. It is given that is known to be within 1 micrometer of a certain point of a band. So that is 1 micrometer is our uncertainty in position. So let us calculate what is the uncertainty in speed. What is the mass given? 500, 8.12. Sorry, so that 8.12. So Heisenberg from that uncertainty we know delta H into delta P greater than equals to H cut by 2. So the minimum uncertainty. So this so so actually some uncertainty here, some uncertainty here, multiplied greater than equals to. So the minimum uncertainty we know that is delta H into delta P H cut by 2, right? Minimum uncertainty. So delta X is given that is 1 micrometer. That means 10 to the power minus 6 meter. Delta P is nothing but the M into delta V. M is given 500 grams. So I can write it as half kg, right? And it is 0.5 kg. And delta V is also given. Oh, delta V we need to calculate. Okay. So delta V would be H cut by 2, 1 by delta X into 1 by mass. The H cut is 6.626 into 10 to the power minus 34 kg meter square second minus 1 divided by 2 pi will be 4 pi, 4 into 3.14, then 10 to the minus 6 meter and 0.5 kg. kg 1 meter is cost. So something like 6.626 into 10 to the power minus 34 divided by 6.28 into 10 to the minus 6 meters second. So a little more than 1 into, so that is 6.626 divided by 6.28, 1.06 into 10 to the power minus 28 meters second. So that is the uncertainty in the speed or in the velocity. Sorry. So this is going to be the uncertainty. So as you can see, uncertainty is very, very less. Why so? Can you tell me why the uncertainty is very less? Even the uncertainty in position is also less.
because we are dealing with
Macroscopic object, right?
macroscopic particles.
Because the mass is very high. So it is something like a tennis ball.
Yeah.
Actually, more than a tennis ball because half kilo. Actually, a
Yes.
deuce ball, to be honest. So that is why you can see that delta x, the uncertainty in position, as well as the uncertainty in the velocity is very less. That is one thing. So what about the second part of this question? That the second part actually deals with a different object. What is the minimum uncertainty in the position? Now we need to calculate the delta x of a bullet. Now the mass is 5 gram. Still a macroscopic object. Still a macroscopic object. That is known to have a speed somewhere between 350.00001 meter second inverse and 350.00000 meter second inverse. That means the uncertainty in the speed is actually 0.00001 meter second inverse. I'll write it here. So maybe this is the first part, and the second part is the mass is now bullet is 5 gram. We need to calculate delta x. Delta v is given as 0.00001 meter second inverse. That is actually nothing but 10 to the power 5, right? 1, 2, 3, 4, 5. Minus 5 meter second inverse. So delta x is similar. H cut by 2, that is 6.626 into 10 to the power minus 34 kg meter square second inverse divided by 4 into 3.14. Now the uncertainty, instead of delta x, it will be delta v. First mass is 5 gram, that is 5 into 10 to the power minus 3 kilograms. What about the uncertainty in velocity? That is 10 to the power minus 5 meters second. So kg gone. One of the meter is gone, second inverse is gone. So delta x is in terms of meter is going to come. And we have it here. We have 6.626 divided by 20 into 3.14. And here we have 10 to the minus 34, and below we have 10 to the minus 8 minus 26. So it is something around 34. Is
Here it is 1.06, similar
yes,
to previous one.
yes. Obviously, there will be some 0. If we think like that, 0.06 into 10 to the power minus 26 meter. Or if I need to take multiply this with 1.06, then we have 10 to the minus 27, I guess. This is something we are going to do. This is also very, very less. Right? This is also very, very less. So for macroscopic object, these uncertainties are going to be very, very less. But for an electron, for a proton, where the mass is very, very less, that is uh, in atomic units, 10 to the power minus 31 kgs. That time, the uncertainty is going to blow up. That is actually will come in maybe in meters, because here it is 10 to the power minus 3 kg and there it is 10 to the power minus 31 kg. So a factor of extra 10 to the power minus 28 is going to come, and that is actually, as you can see, it will become something 1.06, even 10.6 meter. So that is going to happen when we are dealing with electron or uh, atoms. Atoms of smaller, obviously like helium and all. If we think of uranium and all, then also the uncertainty is going to fall. Anyway, what about the next question? 8.12b. 8.12b deals with the similar problem, uncertainty. An electron is confined to a linear region with a length of the same order as the diameter of an atom. So it is said to about 100 picometer. So in easier terms, an electron is to be confined in an atom. So and the uncertainty here is delta X is actually 100 picometer. What is picometer? 10 to the power minus 12 meter. So it is something like 10 to the power minus 10 meter. So uncertainty is 1 angstrom, something like 1 angstrom here. So we need to calculate the minimum uncertainty in position and speed. So we already got the uncertainty in position, right? That is 100 picometer or 1 angstrom. What about the speed? We have the mass, we have the uncertainty in position, we know Planck constant, we know the formula, we'll put it, we'll get something. So we'll not do it here. Okay? Because it will a similar problem. We'll just discuss what does it mean. But here one important thing is there that see the uncertainty of the electron is given by how it is confined in that atom. So confined in the diameter of that atom. So it is inside that atom. That's what it tries to say. So one of the important aspect of the question. What about the next question? 8.13a. In an X-ray photoelectron experiment, a photon of wavelength 150 picometer ejects an electron from the inner shell of an atom and it emerges with a speed of 21.4 megameters per second inverse. Calculate the binding energy of the electron. Again, it is a photoelectric effect problem where the wavelength is 150 picometer. So wavelength is even less. Or not to be less, it is something at 1.5 angstrom, right? So what would be the energy? Uh, Let us actually calculate the binding energy because the second problem 8.13b is going to be the same. So we'll not do for 8.13b, we will do for 8.13a. Let us do this. 8.13a where the wavelength is 150 picometer and the speed of the kinetic, I mean the speed of the ejected electron is 21.4 megameter per second inverse. We need to calculate the binding energy or the work function. So this is the energy of the photon, incident photon will be equal to the phi plus kinetic energy. So that is phi plus half m v square. So the lambda given was 150 picometer, right? So this is 6.626 into 10 to the power minus 34 joule second into 3 into 10 to the power 8 meter second equal divided by 150 into 10 to the power minus 12 meter is going to equals to 5 plus half mass of an electron is 9.3 into 10 to the power minus 31 kilograms. V square velocity was 21.4 megameters. That is 10 to the power 6, right? Meter second inverse square of that, right? So let us go to the next step. So 5 and the binding energy is going to be 6.626 into 3 divided by 1.5 into minus 34 into the minus 26 is become into the minus 26 into the minus 27 into the minus 15. second unit gone, meter gone, and this is in joule, minus 1.2 9.3 into 10 to the power minus 31 into 21.4 square and 10 to the power 12 meters square, second minus 2. Obviously, kg is there. We know what this is, right? This is joules. Kg meter square, second minus 2. Actually, Newton into meter, that is joule. So joule, the unit are same actually. This is nothing but joules. So just play around this and get the work function from it. 6.626 divided by 5, that is 1.3252 into 10 to the power minus 15. And here also it is 2, so I will calculate that. 9.3 into 21.4 square of that into 10 to the power minus 19 divided by 2. In case I am doing it correctly, something down to 2.13 into 10 to the minus 16. So if I have to do that, this is 13.2. 13.2 into 10 to the minus 16, and this is 2.13. So 13.252 minus 2.13, something around 11.122 minus 16. Obviously, the unit is joules. 1.11 into 10 to the power minus 15. I hope I have done it correctly. If not, one can do it. If there will be mistake, there will be mistake in the calculation, but that is not expected. But I guess this is correct. So this is the binding energy in joules. I hope this is correct. And the next problem is similar to this, I guess. 8.13b. So we'll not do that for now. One can do it. We'll go to another operator problem, that is in 8.14a. The question says determine the commutators of the operator d by dx and 1 by x, and another set is d by dx and x square. So actually commutator relationship is something like this. I'm going to explain 8.14a. Suppose we are talking about some commutation relation A, B. If they are commutators, then this is 0. But commutator, what does the question says? That determine the commutator. That actually is A multiplied, left multiplied to the B, minus B was left multiplied to A. That is 0. If A and B are commutator. If this is followed, then you will say A and B are following the commutator relationship. But if in the question they want us to see if d by dx and 1 by x are commutator or not, and in other set you want us to know d by dx and x square, are they commutator or not. So let's see if they are commutator, then let's see if they have a eigenfunction f of x, they are operating on that, right? Minus now 1 by x into d by dx operating on f by x. This should be equals to 0 if they are commutator. But what are we getting? So for the first part, as you can see, it is a derivative d by dx of 1 by x and f of x. So this is something we do the product something like UV method, right? So first we'll do the derivation of this and this will remain constant and this will remain constant and we'll do the derivative of this. So first we'll do derivative of 1 by x and that is minus 1 by x square and f of x will remain same, then plus now 1 by x will remain same and we will do a derivative of f of x, that is something f dash x, right? And then at this part we have nothing more to do, it is something 1 by x f dash x and you can see these are getting cut. So we are remaining with minus 1 by x square f of x. So what actually we are seeing, this is actually not d by x and 1 by x are not commutator, but we are getting something like, so if uh, is d by dx 1 by x operating on f of x, we are getting minus 1 by x square f of x. Okay, this is not an eigenvalue equation that we have to remember. In eigenvalue, this has to be a constant, but this is in terms of x, right? So this is not an eigenvalue equation. What about d by dx and x square? Let us see. So d by dx into x square operating on f of x minus x square into d by dx f of x. Similarly, 2x into f dash x minus, sorry, plus x square f dash x minus x square f dash x. These will cut and we will get 2x into f dash x. So these two are also not commutators. What we are getting is d by dx x square. When they operate on f of x, we will get 2x f of x. Okay, this I have made one mistake here. So this is what the question was. Now what about 8.14b? That is actually a little, this may actually take little more time and with this we are gonna end today's discussion. 8.14b. This is actually, I can also make mistake. Determine the commutator of the operators A and A dagger where A is x plus I p, where p is obviously linear momentum operator, divided by root 2, and A dagger is obviously the complex Hermitian conjugate of that, that is x minus ip divided by root 2. So this may actually a tough, even tough for me also. Let us actually try to solve it. So we need to show the commutator relationship just we are doing earlier on, suppose let us say f of x and we will get something like a dash f of x minus a dagger a f of x. That is what we want to do. Now a is given x plus I p divided by root 2 and a dagger is x minus IP root 2. Before that, we should also write Px. It's a linear momentum operator along x. So that is also given by h cut by I or minus I h cut d by d. Okay. So let us do the first one. What is a dagger? A dagger is 1 by root 2. 1 by root 2 will become 1 by 2. Then x plus I px multiplied by x minus I px. If they were not any quantum mechanical operator, then one could have write x square plus px square. But that is not the case here. They are not any constants. They are operators. So this is 1 by 2. You need to do it. This is actually x square. And then it is minus I x px. Then it is plus I px x. If they were commutators, x and px, then you could have cut it. But x and px are not commutators here, actually. X px, then minus I square px square. Minus I square is actually minus 1. Minus 1 will be plus 1. So I will just erase this and I will write a plus a. I hope you are following. So this is what we are going to do.
Yes, yes.
And what about the another part? A dagger A. Similarly, 1 by 2 x minus I x x plus I x. So that is actually 1 by 2. First it will be x square. Then it will be, I'll do x with IPX plus IPX. So I press I, x is first, px is then there. And then here I, px is first, and then x is there. This is very important. And then obviously the minus I square px square, that's plus px square. Yeah. So this is what operator algebra is like. That is how it is different from normal algebra. So what we have to do? We will put our psi here maybe. So what does px square is? As we already going to have it, what does px square? Px square is minus I square again. So it is uh, plus I square, that is minus is eventually going to come. Each cut a square minus I into minus I, that is plus I square, right? So each cut a square d2 dx2. Right? So this is what we are going to have. So what does a dagger f of x will stand for? That will stand for 1 by 2 x squared minus I x dx plus I px x plus px squared f of x. So before that, I guess it is better to see what x px are when it will work on f of x. So I'm just doing it because we will see why we are doing x px of f of x minus px x of f of x. So x into minus ih d by dx of f of x, and here it is minus I, so I plus ih d by dx of x f of x, the whole, right? Because it is there on the right hand side of the dy. What we are doing in the last problem, right? So minus ih will come here. It is x if dash x. What about this? First we'll operate on x and then f of x. I h cut. If it is of derivative is x, then we are going to get 1. So it is f of x, and then the next will be, if we keep x as it is, then we are going to get the derivative of f of x, that is f dash x. So actually that is cutting, and we are actually getting something around ih cut f of x, a commutator relationship of it. As you can see here, it is minus ixph. So it is minus, so minus x px of f of x is obviously going to be minus ih cut f of x. I just done it because we are going to simplify this part. Half x square is the x. Here we are going to get minus ih f of x for this part. I'm highlighting it here. Maybe I should highlight with a different color. This part I could write it like this. That's what I shown in the right hand side. And this is plus px square f of x. I'll not do much here. Okay. This is from the this side. What about a dagger a f of x? That is half x squared plus I. Oh, I missed one term. See, that is one mistake. So I missed this I, right? So it would be I square, right? Let me maybe write it better. So I have done one mistake. So this I was there. Just with x and px, I was there in both the cases. It's like I am multiplying this with I, nothing more than that, right? So that is actually minus I square. So again, it is minus 1, it will be plus something, right? So should I write it there? I guess that would be easier. X square plus h cut plus px square f of x. I think this is much simpler and this is something different. We have done it here. So let me have it in a bound. So the next part is I. So now we are discussing A dagger A when it is operating on f of x. I x p of x minus I p of x plus px square operating on f of x. As you can see, this is straightforward half I square h. I was there. This is this. IH f of x multiplied by I plus px square. F of x is outside. So it is half x square minus h plus px square f of x. So what do we have finally? So a dash f of x minus a dagger a f of x is half x square. Then we got plus h cut plus px square f of x. And here we have minus half x square. Here we got minus h plus px square f of x. So it is clear that this plus x square and this minus half x, these are going to cut, right? So I believe uh, let me write it down, or else maybe I know after all these calculations, this part seems to be little easier. It's all about calculation. As you can see, if I choose a different color, then this and this is gone, this and this is gone. So we are left with h cut by 2 f of x plus h cut by 2 f of x, which is h cut f of x. And that is nothing but, so if I write it in this form, a dagger f of x is left with h cut f of x. This is actually a eigenvalue equation because h cut is constant, right? So the commutator of a dagger is h cut. I know there was a lot of calculation, but this is what we are left with. Where obviously we should not forget what a and a dagger are. A is 1 by root 2 x plus I px. A dagger is 1 by root 2 minus I. this is what we should not forget. This is not true for any data, right? Any operator. This is for this particular operator. This is true. So is this understandable?
Yes, yes.
Okay. Thank you. And with this, actually, I am going to close today's session. But what, as you know, that in class, I guess week one lecture, Professor Datta has already discussed about the solution or the Schrodinger equation of, I think, the particle in a box problem, right? And there are some obviously assignments are due tomorrow. So it is always best to do as many numericals as you can. And so you can try out these problems, what is right now I'm showing on the screen. These are also from Atkins Physical Chemistry 8 edition. And actually, we are going to solve these questions on the next session and discuss some of the lecture notes also. And with that also, I'm going to share these notes in with the slides actually. Um, this tutorial problem that you can check out. So that will, some operator related questions. So that would be beneficiary for you, and will solve these problems also. May not We may not be able to solve all the problems, but we'll be able to solve some problems. Okay. So with that, I am stopping. I'm stopping sharing. Stop presenting my screen. Okay. MM, I guess if you heard the last means you could hear after rejoining maybe. Okay, okay. Thank you for confirming. I guess the session was useful and beneficiary to you, and hope
Yes,
to see you guys again in the next session. And we will solve those problems from where we are leaving them right now. Try to solve them by yourself. And if you have any doubt, post it on the discussion forum. I guess you know how to reach out the discussion forum.
yes,
Okay, good. So you can always go to the discussion forum and post your queries. Other TAs are also there that who will help you with your problem. Um, so with that, we are going to stop today. Thank you for joining. Good night.
thank you, thanks.